Okay, so I'm really grateful to Mariangela for starting this tradition of setting you homework problems, because I know for some of you this has made you think a bit. And so the question was, I give you a vessel of steam that I've prepared in one of two ways, either with a heat bath that produces it in a mixed state, it's entangled with the bath, or by exciting it in some coherent way, and so that it's in a pure state. And this pure state you can think of as being sort of chosen more or less randomly from the ensemble. And so these are the fundamental description of these looks very different. I give you the vessel, and I first give you just one copy of the vessel, or one of each. And you're free to make any kinds of normal quantum mechanical measurements. You can measure over and over again with that same vessel. And the question is, can you tell which one I've given you? So does anybody have a way to do that? John does. Do you? Okay, what do you mean by normal? No, because you need two copies. Yeah. I give you one copy of each. I give you one. Good. So you're jumping ahead. Right. So the answer is no, you can't. And the basic reason is that for complicated systems, I guess technically for quantum chaotic systems, for systems that exhibit thermal behavior, all ordinary observables in a random pure state look like those in the ensemble to very high accuracy. So so for any normal observable, so the measurement in the pure state is equal to the expectation value in the density matrix to accuracy, which is really exponential in the number of degrees of freedom in the system. And this principle has been formalized, actually a special case where the size or energy eigenstates, as the eigenstate thermalization hypothesis. Actually, since once something is understood, it's much more interesting to find exceptions. One of the big excitements in condensed matter physics these days is systems that exhibit many-body localization, where this is violated. And these are systems which actually don't thermalize. But one is deliberately looking there at exceptions. This is what happens to steam. This is what happens to any ordinary complex system. So the answer is no. You're limited basically to measuring, say, a projection operator, some linear operator, and there's a small difference. But if you think about it, I would need to give you e to the s systems, a huge number, before you could get the statistical variance down to where you could distinguish between that and that. If I gave you e to the s systems, you could probably also do other tricky things. You could probably also measure, say, a lot of different operators and a lot of different bases, basically measure the whole density matrix, one element at a time, and then calculate trace rho log rho. You could if I give you enough copies of the system, you can answer the question. So there are actually sort of several reasons I think this is a good question to think about. And the first is that when we learn stat mech, when we teach it, the course is usually all about ensembles. And it's rarely emphasized that it's also true of individual pure states. Basically, one way to think about it is for a complicated state, when you measure one aspect of the state, for a complicated system, when you measure one aspect of a system, the rest of the system is playing the role of a thermal bath. The physics is not that complicated. Now, this is true for typical operators. There are very special operators. There are very special operators that if I told you what the pure state was, you could simply measure this projection operator. That's an observable. That's a projection operator. And it's clearly 1 on this state, and it's very close to 0 on that state because it annihilates all but one term. So this holds for typical operators, and the conditions of the problem were that I didn't tell you what state I prepared, so you don't have that option. Okay, but now, okay, I explained how if you have e to the s states, you can do it. How about if I give you 20 copies of A or 20 copies of B? And there's a reason I'm picking 20. And the 20 doesn't unlike e to the s, the 20 doesn't scale with the size of the system. Okay, did anybody come up with a strategy for that except for John, who's already said the key word? So let's consider the case of system B. I give you 2 copies, and so my combined system is psi. And let's consider the swap operator, which is defined. So Z is the swap operator. Z on psi1, psi2 is psi2, psi1. So now if you think about it, the eigenvalues of Z are plus and minus 1. The eigenvalues. All right, you diagonalize this operation, and it's either plus 1 or minus 1. And clearly Z gives plus 1 acting on psi. So trace of rho BZ is 1. Trace of rho AZ. So as I run through the ensemble, actually, it's not rho B. It's trace of. I've got 2 copies of rho B. So it's trace of the 2 rho B times rho B Z is 1. Trace of rho A times rho A Z. Okay, so each of rho A's is an ensemble, and as I run through the ensemble, I almost always have a different state here from here, and so I almost always simply get 0 for the trace because this swaps the 2 states, and I take the inner. Essentially, I'm getting plus 1 and minus 1 with essentially equal probability. Essentially 0. Okay, so if I give you 2 copies of the system and you measure Z, okay, here you're going to get 1 always. Here you're going to get 1 half the time and 0 half the time. So if you get 0, you know that you had the mixed state. If you get 1, well, you can't be sure whether you had this state or that state because this has a chance of returning 1. However, if I give you 20 copies, 10 pairs, you do this 10 times, and if you get any minuses, you're in the ensemble. If you get 10 straight pluses, well, you could be here, or you could still be on the ensemble, just very unlucky, a 1 in 2 to the 10th chance that the coin has come up. And so this is called the swap test. It's a standard bit of quantum information. And again, I haven't thought carefully about whether there are other strategies. I suspect, from what I know, that this is optimal. Good. And so there's so the first lesson is again that thermal behavior isn't really about ensembles, and there's a formalization of that. The second is just this little bit of quantum information. Okay. The third lesson is suppose that I heat the system up a whole lot more so that the steam collapses into a black hole. And now I ask you the same question. And the answer is the same. I can prepare the black hole through coherent operations in a pure state. I can prepare it through a thermal bath. Very different density matrices, but all of the same properties with respect to almost any, with respect to all but very special quantum measurements. So one reason for doing this is that to correct the misapprehension that one occasionally hears that black holes must be in ensembles. They can't be in pure states. Obviously, they can be in pure states because I could take a system at absolute zero and again carry out manipulations that don't change the purity, but that raise its energy to the point that it collapses. So that's the third lesson, that black holes sure can be in pure states, and all of the same words hold. And the final lesson is, remember the original Hawking paradox. So the original Hawking paradox, we start with matter in a pure state, and let it form a black hole, let the black hole evaporate. We can be doing it all inside a vessel. The vessel might be anti-de Sitter space. And the question is, how do we know, what's the experiment we do to determine whether information is lost or not, whether the final state is pure or mixed? And here is the simplest thought experiment that you could do. Again, you do the same process 20 times with the same initial state, and then you carry out the swap test on pairs, and it tells you whether the final state is pure or mixed. So in the last lecture, Shanta was, I think, saying that this was getting into issues of interpretation of quantum mechanics, and I disagreed, because my understanding is all interpretations of quantum mechanics give the same answers for measurements like these. And here's a measurement that you would make that would distinguish the cases. But although it doesn't use interpretations of quantum mechanics, it uses quantum information theory, because quantum information theorists have been spending the last 20 years figuring out clever tricks like this for making maximal use of the information in a quantum state. Question?
So, in a practical case, though, if I have two boxes of gas,
yes,
I'm not going to be able to do this swap thing.
Right. This is well, actually, good. So again, this is a. Sorry, go ahead.
Is there like a sort of approximate thing that you can do that will get you like near that you can actually do on a physical system?
So indeed, we're very much in thought experiment land, and that's but the reason for doing this is because we're trying to learn what are the basic principles underlying our system. In fact, cold atom experimentalists are starting to get to the point where they can manipulate quantum states. So they're now doing the swap test on systems of 4 cold atoms. So that is they're limited by statistical noise and stuff. But I think it's pretty cool. I mean, they can control the quantum states of these things with such precision that they can literally. Well, I think John was complaining it wasn't exactly the swap test because it was some proxy for the swap test, but I'm not sure. But yeah, I mean they're essentially doing this, and they're doing it with 4 cold atoms a day. Maybe they'll do it with 1,000 cold atoms, next year. Doing it with a black hole, there are a number of technological, things one has to deal with first. But yeah. Question, yeah.
Person doing this swap test.
Yes. So, see. The thing about quantum, the way I understand, well, I guess this depends on whether you're a Bohrian or a many worldsian, but whichever you are, your interpretation has to reproduce the idea that, I mean, we know by observation that quantum mechanics is probabilistic, that if that you get 50-50 probability when you make measure. So again, this is a measure when you measure a Hermitian operator. And by the way, I could go further into what one means by measurement. I mean, one way to think about measurement is you have your system, and then you have some operator you want to measure in the system. So what you really do is you add to the Hamiltonian a coupling between that operator and some part of your apparatus. And so initially the apparatus is in some initialized state, some definite state. The effect of the coupling is that this will generate correlations between the eigenvalue of the operator and the state of the apparatus, where the dial points, and then you look at the dial, and whatever your interpretation of quantum mechanics is, the outcome should be that you see the different dial positions corresponding to the different eigenvalues with the usual probabilistic law. So I haven't answered your question, but that's how I'm thinking about quantum mechanics. Well, I don't know if it's every interpretation agrees with. I mean, you can't get around the fact that quantum mechanics predicts probabilities for real observers, whatever your interpretation. And I think all the interpretations give the same probabilities. Okay, any questions? Good. Well, not good, but anyway. Yeah. So when the question was rapidly asked, how many copies do we get? I thought that Henry, knew about the swap test. It's buried in Harlow's notes, for example. He mentions it, but pretty briefly, not at this level of detail. I actually think that I was skeptical for a long time that I thought we all understand quantum mechanics. We don't need quantum information theory, but there's tons of insights and like this that have come out of it. Yes. Right. That's right. I'm not sure if you can do a little better, maybe by using more elaborate permutations. That's a good. Yeah. So now let me sort of review where I was last time. I was talking about the various black holes in anti-de Sitter space, and in one case we had increasing energy, and in one case we had increasing temperature. So these are like the microcanonical and the canonical ensembles. And in this case, we argued for two-phase transitions. The gas, the 10D black hole, and the 5D black hole. And in the thermal ensemble, in fact, there's only two phases. There's the gas and the 5D black hole. The point is that when the black hole is much smaller than the space, you run into this negative specific heat for the black hole. A light black hole has a much higher temperature than a big black hole, and so that's not thermodynamically stable. And so this is the picture. The question was asked afterwards, hey, wait a second. This is a conformal system. The one thing we know about conformal systems is they have no scale. So how can the qualitative physics depend on the energy or the temperature? Now, somebody must know the answer to this. Yeah. So right. So this whole discussion was in the context of global anti-de Sitter space. In global anti-de Sitter space, the field theory lives on not on Minkowski space, on a three-sphere And so it has a radius, indeed. And all temperatures are measured relative in units of that radius. And again, there's a famous paper by Witten that's cited in the notes that first made this observation. Well, I guess first made this observation in this context. Also, the fact that this transition existed on the gravity side was discovered many years earlier by Hawking and Page. So they appreciate, long before ADS-CFT, there was some appreciation that ADS was a good way to put your system in a box. Okay, good. So now coming back again to our goal of sort of making precise now the information theorem, the information puzzle. So the simplest thing to do would be to start with a black hole down, a small black hole, one which is small enough that we're down here in the gas phase, meaning that the black hole will decay completely. So we initialize it by throwing in some quanta, make a black hole, let it evaporate. Good. And then again, the logic is that, trusting the duality at the level I claim we should trust it, pure states must evolve to pure states. Just another aside. So like at very high temperature, again above the transition from the gas. Again, the fact that the typical state is a black hole is just the statement that black holes are, at least at sufficiently high temperature, they are the duals in the deconfined phase of the field theory. Black holes are the duals to the thermal ensemble. So the duality kind of mirrors very much this intuition that all thermal systems should be the same. Here, black holes are literally dual to thermal states. You can also, although the large black holes don't decay in the normal way, they're still actually, because they're states of thermal equilibrium, they're actually the nice setting for thinking about a lot of the questions. I won't go through it here, it's in the notes. Maldacena pointed out that there is an analog of the information problem for this, for this case, where if you look at, well, actually it's effectively the point is this: quantum field theory as an effective, quantum gravity as an effective field theory gives you a continuous spectrum, while the gauge theory, any normal physical system in a finite volume gives you a discrete spectrum. I talked about that a little bit a couple of lectures ago. And so there are versions of the information problem which are just the question of where does the general relativistic argument that the spectrum is continuous break down? How does this again is a very pure form of the information problem. How is quantum gravity modified from just Einsteinian gravity in such a way as to give a discrete spectrum? It's a really good question. It has to have an answer. Okay. Question, please.
So sometimes the Hahn measurement is used to define like with states.
Yes. Yes.
How would that compare to like states?
Wait, which one? Sorry. Oh.
Like a scholar.
Wait, so. So this is a good. Right. This is a good question because most of the theorems are going to, as you say, about Haar random states because that's it. You can prove stuff about that. Even in my example here, you really can't. I don't. Well. So right. The claim is that it takes an exponentially long time scale to produce a truly Haar random state because you need a sort of large number of observations. I think the claim is also, and again, this gets into quantum information that I don't really know. But the claim is also that with a much smaller number of operations, you can generate a set of states which is Haar random for, let's say, all practical purposes, such as this one. And I can't quote the theorem, but I've heard this assertion. And again, a state which I form by heating ice with a laser, that's not a very hard random process. But I think the expectation is that in a system which is, truly chaotic, it's as random as any other state. I don't think, probably hard to prove that, but yeah. Okay, so let me just make sure I didn't have more to say before I go on. So, yeah. So we're in this funny situation where we have we just follow our nose, quantizing general relativity, and we conclude that information is lost. And it's really a pretty simple and compelling calculation. And then we have a whole bunch of reasons, for thinking, no, that shouldn't be that way. And again, there's the practical difference is, again, you actually can measure with the swap test. Good. So it's a meaningful distinction. So now how are we going to reconcile these things? Where is Hawking wrong? If he's wrong, as I believe, and he seems to agree now, and we don't know. So Susskind and I guess also Tuft and Preskill put forward a scenario which says that the paradox is not as bad as it seems. So let me draw my horizon and some space-like slice. And now let's go back to my experiment where I threw in, I had this entangled pair of bits, Q1 and Q2, and I keep Q2 on the outside. This is Q2, and I throw Q1 in. And and then there's some later Hawking radiation. And if I want information to be not lost, I need the final state to come out in a pure state. So Q2 and Q1 are entangled, but I also need that Q2 is entangled with the Hawking radiation in order for the state to be pure. And this is not possible. Again, it's strong subjectivity, but just very simply, if these are in a pure state, the wave function with this is a product, and so it can't be entangled, and vice versa. So again, a number of Preskill, Tuft, Susskind made the observation that, well, it's a little bit hard to represent on this slice, but provided, I should probably draw the slice as kind of a bit kinked, but provided that this is sort of the clone of this. I'll call this provided the clone of the information comes out somewhat later than this bit was thrown in, no single observer can actually see both bits, because what they would have to do is they would have to measure this bit, jump in, and then measure this bit before this bit hits the singularity. And in fact, and that's, as you can kind of hard. In fact, if you work out the geometry, which I won't do, as long as the delay between throwing this bit in and its clone emerging is greater than the scrambling time, which is something of order the basic unit, the Schwarzschild radius. Here, I'll write that bigger. The basic unit R sub s times log of R sub s over L Planck. As long as the delay is at least that long, then no single observer can see both bits. And so maybe there wasn't ever really a paradox. That is, you can make everybody happy, you can keep the entanglement that the Hawking process generates and still have a bootleg copy of the same entanglement appearing later. Now, if I really, so this one of the nice things about this paradox is it brings us to what is the basic framework for quantum gravity. Because the basic framework for quantum gravity as an effective field theory is you would have a state on any space-like slice. And if that's true, what I've drawn here is forbidden. It violates strong subjectivity. You can't have this double entanglement. And however, because of the operational thing, it suggests that maybe, in fact, we shouldn't be thinking of a fundamental Hilbert space which is so big. We should only be thinking of smaller Hilbert spaces which are just large enough that one observer can see them. And that's black hole complementarity. And there's kind of two versions of that. In one, there is a single overarching Hilbert space, but, well, let's put it this way. There's only one copy. There's only one copy of this bit. But there's a strong relativity principle in that different observers see that bit in different places. There's a strong breakdown of locality. An observer who jumps in sees the bit here. An observer who stays outside sees the bit here. So one is preserving quantum mechanics at the cost of a large violation of ordinary local physics. And actually, so this was done in '93. Maldaceno's duality was about 5 years later, and again, it seems to tell us information not lost, but it seems to fit with this because in Maldaceno's duality, you have the boundary description and you have the bulk description. So you have two descriptions of the same quantum excitations in very different places. And so this, again, it's not exactly this, but this seems to accord perfectly with that intuition. That in ADS-CFT duality, space-time, the bulk space-time is emergent. It's not fundamental, so we shouldn't expect perfect locality. And moreover, again, in different duality frames, you can see things in very different places. So I have to say, for me, this was compelling. I figured the whole problem was done with. So what happened? Well, actually, before I say what happened, let me sort of give a few more ideas that go along with this. The first is there were a number of things that were widely believed, and Susskind and collaborators enshrined them as postulates. So the first is purity, which is that there is a black hole S matrix, meaning that there's a quantum mechanical S matrix that describes formation and evaporation of black holes. The second was, I'll call it quantum gravity as an effective field theory outside the black hole. Or I could say quantum field theory and curved space-time outside the black hole. The third, which doesn't appear so directly, but it's important, is that e to the Beketin-Hawking entropy really is the number of states. And the fourth is that an infalling observer sees no drama, sees just ordinary laws of physics, and no particles where the adiabatic principle wouldn't have you see particles. And again, so this is kind of a more formal statement of what's above. There is something spooky going on, but it's not observed. The basic point is it's not visible to any single observer. There's another sort of subtext here, which is that. So here's the horizon, and here's a surface that stays sort of a Planck length outside the horizon. Because of the conformal diagram, it doesn't look like it's staying a fixed distance, but it is. So this is this. So imagine that we have so we imagine a shell slightly larger than the horizon, and the idea is that seen from the outside, this acts as some kind of membrane, which absorbs whatever falls into the black hole, processes it in some complicated way, and then re-emits it later on. And that's what the outside person sees. And that actually fits with the fact that there's this black hole membrane paradigm where just for very practical classical calculations, the black hole horizon behaves like a dissipative membrane. So outside, so in terms of this assumption that quantum field theory is good outside the horizon, basically the assumption is nothing funny happens outside the membrane here, but from the point of view of the outside observer, there is some complicated process. Whereas for someone who falls through, they're in a different duality frame. They don't see the membrane, and so that seems kind of compelling. But it would be nice to make it precise with some kind of model at least. And I tried for many years to make models of this membrane and other kinds of models that I'll tell you about, and failed. And this ultimately led to a no-go theorem, which is this firewall argument that I'm about to tell you about. But it didn't begin as a no-go argument. We didn't set out to say we're going to prove a no-go theorem. We went out to try to do something, and after failing enough times, the point. And I think this is how most no-go theorems arise. You try to do something, you fail, and eventually you figure out you're failing for a reason. Good. Now, so I mentioned one model that I tried without success. Let me mention another model. It's I don't know how important. I think it's useful. It's always I don't know, but I always make progress in problems by finding the simplest possible system that exhibits whatever it is I'm trying to understand. And here's another simple system. We're going to just model the Hawking radiation. It's called a bit model. We're going to model the Hawking radiation by just a line of quantum bits, each of which can be in a state 0 or 1. And this dividing line here is the horizon. So on the outside, we have, from the outside, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6. And on the inside, bit 6 tilde, bit 5 tilde, bit 4 tilde, bit 3 tilde, bit 2 tilde, bit 1 tilde. So what happened, if you think about the Hawking process and these long slices that I talked about are producing these entangled pairs at the horizon, produce a pair, it moves out, a new one of pairs. Question, John? Yes? Outside the stretched horizon, right.
So, but in this picture, aren't you building in quite a bit more than that?
Well, this picture is a very coarse picture. I'm not sure. This picture is an extraordinarily coarse picture.
I'm happy with coarse, but you're including stuff that's past that.
Well, yeah. So what? So I want to good. Yeah, actually, good. This model does not incorporate this principle. I want to actually good. I want to start with this model. And then, good. Yeah. This model is describing more than a single observer can see. Good. But it's a model that's good. But this is sort of this is a toy model of what the black hole does. And so at the next time step, we will insert another entangled pair. And this leads to the problems that I've talked about. The inside Hilbert space is much larger than postulate 3 allows. And also, there's this large entanglement which leads to the information problem. So if you want to try to make a model that that doesn't lose information, well, here's a different model. At the next time step, we delete the two inmost bits and insert them here. So that you see what is on the inside, I've chopped off 2 bits and inserted them in such a way that one stays inside and one gets out. And now this is what one needs because now the inside is getting shorter as the black hole evaporates. And by the time the black hole has finished evaporating, everything inside is gone. It's been re-emitted to the outside. So this is a set of models that Mathur and Giddings developed. You can elaborate. For example, you can toss in various kinds of unitary operations acting, say, on the inside. And it's kind of nice because if it's nice having a concrete model like this because it gives you some grounding. If you think you have an answer, you can see can work at this level. Now, as John has as John has said, this model describes much more than complementarity allows because it describes all this stuff. And so we should try to make a complementary bit model which only captures what a single observer can see. What can a single observer see? A single observer, in principle, can see all the stuff that's already come out and then jump in and see 1 or 2 bits. So a complementary bit model would have other pieces describing what the inside observer sees, but it would describe only this much. And now this comes back to something I said earlier in my talk, that a lot of the traditional discussion of black hole quantum mechanics is focused on this nice slice. Mathur really focused on the fact that there was a paradox right at the horizon, this strong subadditivity, because you really have 2 choices. You can add an entangled pair, and then the problem is that you keep rising on the Hawking curve. You don't go down on the Page curve. Or you can insert an unentangled. So you can you can insert sort of the usual thermal entangled pair, 0, 0 plus e to the minus thermal factor 1, 1. Or you can insert an unentangled pair, say just 0, 1, or any unentangled pair you like. And this pair is what the Hawking process gives you, and it gives you the bad effect that the exterior von Neumann entropy keeps rising. The exterior von Neumann entropy doesn't keep rising. In fact, you can make it decline. But the cost is that you have a severe modification of quantum field theory in curved space-time right in the neighborhood of the horizon. And that's really what it comes down to. The Hawking, you have these subtle swap tests and things. If you actually try to make a model that emits the information, you find that you're making actually order 1 modifications of quantum field theory in curved space-time in the neighborhood of the horizon. This is what Mathur called you can't have an information-free horizon, and it's a good expression. I'll use it again tomorrow. Now, this bit model, very quickly tells you that the problem had nothing to do with this non-complementary stuff. It's visible to a single observer, and basically the final argument is simply taking this basic point, and now this model is very coarse. These bits are sort of a Schwarzschild radius apart, and so it's going back to the actual system and asking, what is the implication? So, John, was a question?
Can't I complain that you're still including non-complementary stuff?
I don't think you can. What? In what sense is it non-complementary?
That one bit that you put there.
No. I can measure the outside stuff and then jump in.
It's still not outside the special range.
No. But it's visible to a single observer.
Not all of that is visible to a single observer.
Yeah. They can measure. Yes, it is. Why not?
Well, okay.
If these bits were not all visible to a single observer, there would not be a paradox. I agree, but I think that, but why, they come out in succession. Yeah, it's just, But no, I say, I'm talking about here, the thing here I'm saying is no drama for the inflowing observer, because the inflowing observer has the right to measure the stuff on the outside before they jump in. So this line of thought leads you to conclude that the inflowing observer sees something bad, whether it is a violation of quantum mechanics or whether they burn up. They see something bad. So, good.
Can we a small part of the 2 years of arguing about this a little more?
Well, so
I mean, so it's the statement.
yeah, you could say anything you want while I'm erasing. How about we make that deal?
Good.
Yes.
So the inflowing observer, the statement that the inflowing observer can measure all that stuff.
Yes.
Seems really right.
Yes.
In particular, it seems there's a great deal of power to that observer.
Yes.
Actually do all the stuff
Right.
and remember all the information.
Right. That's right. Right. Good. Okay, so what you're saying, I mean, is similar to the point made by Hayden and Harlow. That is, right. So the paradox arises assuming when you have this observer who can make all these measurements. And there are two ways to think about that. The way I think about it is the following. It's important to focus on operational things like this. But if you decide that you can't do something operational, you have to decide, is this just some annoying practical problem or does it point to a deep principle? So you still have to say, how are you going to, what is your theory of quantum gravity if it somehow is built on the idea that it's hard to measure all these bits? It's some course in it. I don't know how to think, but in fact, if you put your black hole in a de Sitter space and you allow yourself the power that ADS CFTers usually allow themselves, which is to manipulate the boundary conditions or the Hamiltonian of the CFT arbitrarily, you can measure all these things because, they come out, these come out to the boundary, you capture them, you measure them, and then you jump in. So yes? Please, yes.
Because you're talking about an observer who falls in, and a real observer capable of doing observations is still that radiation, very low energy thing. So I can imagine that your argument would work if nobody's there to look at it. Introduce anyone who is able to see anything. These arguments go away.
I disagree. Now, well, there's so part of the question is what constitutes an observer. Is a single photon an observer? I mean, this is kind of or does an observer have to have a memory? Does an observer have to have a soul? I think Juan, for example, has expressed the opinion that an observer has to have a soul. And maybe he's right, it's true that it raises that kind of question, which is the kind of question that I hope we don't have to think about, and so I'm really thinking more in terms of what is the mathematical description of the theory that would, in some sense, I'm thinking, what is the underlying mathematical description of the theory? So is it one big Hilbert space with different sort of operators for different spaces? Is it smaller Hilbert spaces that single observers can see? How are we actually going to build a theory of quantum gravity that somehow takes advantage of these limitations? And it's true. Maybe that's the answer. And like I said, Juan is partly on your side, but that, he's very bold in his speculations. That part of the issue is that an observer who can measure these things is so large that we have to take into account their perturbations on the geometry. Now, tomorrow, in the context of quantum chaos, I'm going to give another version of the argument that I just gave, which again, it actually leads to the same conclusion that I've come to, and I don't know, well, it in some sense deals to some extent with the perturbation of the observer acting on the black hole. It incorporates to some greater extent. So let me come back to this, and there was another question?
Yeah, so I guess one comparison I had heard, which
Yes.
maybe you could comment on in terms of the operational question.
Yeah.
Is, like, if you didn't know some stuff, you might
Well, sorry. So, good. So the Heisenberg uncertainty principle is a good analogy because, I mean, the uncertainty principle is important, but it's important. It's not sort of the theory. The theory is the Hilbert spaces and the operators. And so once you discover a potential observational limit, that's kind of what I've been saying, and I'm not sure if it's the point you're making, but once you discover a potential operational limitation, you have to ask, what is it pointing you to in terms of the actual form of the theory? Yeah.
But you agree that if you can't demonstrate a paradox for a single observer, then you don't need to put that single extra bit behind the horizon and the paradox goes away.
So again, I think in the context of ADS-CFT, I think I can do everything I need to do in several different ways. But I want to give, again, tomorrow I have a new favorite form of it. There's many ways to make the same argument, which I'm not going to give you most of. But tomorrow I'll give you my favorite new form of the argument because it's very visceral for me. It's what actually convinced me that maybe the firewall really is there. Okay. I've never really believed the argument. I'm with you. I've never really believed this, but now maybe I do. Okay. So I haven't actually got. So I mean I've gotten very close. So again, here is the picture we've seen before. We have the bit inside. We have this bit. We have the early radiation, and at least superficially, and for the purpose of the rest of today's lecture, we will assume that a single observer can measure all of these things. And if the assumption of no drama assumes that normal quantum mechanics holds for them, which means they cannot see both B entangled with B tilde and B entangled with E. And so either we lose the entanglement of B and E, which means we lose purity, we lose the black hole S matrix. So if we lose this entanglement, we lose purity. And if we lose this entanglement, then what that means we no longer have the free. So this entanglement comes from the assumption that we have the free field vacuum for the infalling observer. If we lose this entanglement, we're no longer in the vacuum, and so we lose. We have drama of some sort. Where have I used the assumption that effective field theory is valid outside the horizon? Well, I've used it in the following way. What I call the mode B actually is different in different parts of the argument. For the infalling observer, it's sitting very close to the horizon. When we talk about the black hole S matrix, we're meeting it way out here much later on, asymptotically. And within quantum field theory, as an effective field theory, this just propagates freely to a high order of accuracy, and so that those assumptions are fine. And so assumption 2 to break down would require some effect that basically interferes with the free propagation of this particle, and which it does it at an order 1 level, because it needs somehow it needs to change some. One of the things about this, there are lots of small numbers, e to the minus s in the black hole, but in the Mathur argument and the subadditivity argument, the subadditivity is violated by an amount of the strong subadditivity is violated by an amount of order 1, or more graphically, the Hawking curve goes up and the Page curve goes down. You need an order 1 effect. You're not going to get from here to here by small quantum gravity corrections. Okay, so that's the assertion that these either we lose the first entanglement, we lose the second entanglement, or there's something funny that happens that in the propagation that allows us to have both. So I'm going to talk about those in more detail now. Assuming this is right, what's going to happen if we give up one or the other of these assumptions? Questions? Yes.
3 is there to rule out remnants.
3. Well, so actually, 3 rules out remnants. Although the way one, I took these word for word, not here, but if you take them word for word the way Lenny posed them, 1 also rules out remnants. The way he stated it. But you're right. I mean, it'd probably be more logical to say that 1 rules out information loss and 3 rules out remnants. But just as a matter of semantics, remnants were already ruled. He phrased 1 in a way that also rules out remnants. But you're right, actually. Remnants would. So I guess let's actually do the logical thing and say that 3 says no. 3 is tantamount to no remnants. Remnants would be an alternative as well, because the whole argument is based on the fact that the Hawking curve goes up and the Page curve goes down. But with remnants, the system is, and with remnants, things keep going up. The entanglement to the inside downside keeps going up. So there, remnants is one way to avoid the contradiction. And you're okay. Good. So good. So there's the so what to give up? So if we give up number 3, we get remnants. And again, I think these are ugly and potentially inconsistent for a large number of reasons. And ADS-CFT doesn't do them. I don't have anything to revisit here. Also, number 1. Let me number 1, information loss. Again, the reasons for disbelieving this. If we give, so this is what we're giving up, number 3 or number 1. If we give up number 1, we get information loss. And again, there were these arguments that we went through before ADS-CFT about which is worse, remnants, information loss, or information not being lost. I have to say that Bill Unruh and Bob Wald are happily saying we told you so, because they've never stopped believing in information loss, and they take the firewall as confirmation that they were right. I still don't see any. I view these as, well, this is my own. I view ADS-CFT and the complex ideas that come with it as sort of a step forward, and I view these as attempts to cobble together a barely functional version of quantized metrics. I don't see this as a promising direction. This is sort of like when quantum mechanics came along trying to save classical mechanics. That's just my own gut feeling about both of these ideas. Now, can we give up effective field theory outside? So actually, when we first hit on this paradox, this is what I assumed was the weak point, because in ADS-CFT, space is emergent. Look, the interior is emergent. It's not fundamental. Locality is not fundamental. So why should there be perfect local physics outside the black hole? But the problem is, as already exemplified by the bit model, it's not a small change one needs. One needs basically an order 1 change in the predictions of effective field theory in a region where effective field theory should be valid. It's not a tiny change, it's a big change. An example of a model like this would be you have the black hole, it emits the Hawking photon. The Hawking photon is entangled with its partner on the inside as required by the Hawking process. And then when you reach something like 5 times the Schwarzschild radius, this gets sucked back into the black hole, and you emit a new thing that looks just like B, except it's entangled with the early radiation. That would be a model that does what you need. It's an example where you have, it's an example where there is macroscopically non-local physics, which makes an order 1 change. Another kind of example, which is something that Giddings has largely developed, is you have the Hawking process, but then you have additional non-local processes that produce additional outgoing radiation. And the idea is that this additional radiation carries away information faster than the Hawking process is destroying it. And first of all of the ideas that have come out of this subject, this is the most radical in terms of the properties of real black holes, because if you start messing with effective field theory at this order of magnitude, it will affect all of the classical properties of black holes for near horizon physics. But I actually don't think these. First of all, I find these unappealing. Second, I don't see how you would get them from a more fundamental framework, and I think you can defeat them. For example, you can with Giddings extra radiation, that the idea of which is that here's your Hawking curve, here's your Page curve, and what Giddings extra radiation does is it pulls you down to the Page curve by emitting information very fast. I think you can always find ways to defeat this. For example, you can put a partial mirror around the black hole that reflects back Giddings extra radiation, but not the Hawking radiation. They have different spectral. They have to have different spectral characteristics. So I actually think that this is not workable, even though intuitively it seemed consistent with the idea of ADS-CFT that space-time is non-local.
Any individual idea for trying to figure out how to fix the problem doesn't mean this isn't the wrong solution.
That's right. No, I haven't. It has not been ruled out, but I think there's a sort of a characteristic set of reasons why it doesn't work, and I'd be happy to be shown to be wrong, but yeah.
Can I
Yes.
push on that?
Yeah.
Because it does seem to me to be a weak point of the argument. Part of the weakness that I see is I'm not quite sure what effective field theory in quantum gravity really means. And for example, I know when I do a two-slit experiment, if I actually observe whether the thing might fit or not.
Yeah.
You can't have a system which says it evolves in a certain way, irrespective of what an observer does here. And you are introducing an observer who makes an observation and gets a contradiction.
Wait.
And still
Yeah.
saying it's described as though there was an observer there.
So good. So I mean, basically, that's right. Right, and so right, there are various points at which one can ask. I mean, right, if the observer jumps into the black hole too early, they increase its mass. Therefore, it now is in a much larger Hilbert space because the size of the Hilbert space grows with the mass. And so, and once you do this, you lose the whole argument because what you were trying to observe is now embedded in a much larger Hilbert space. And there are some fairly basic checks one can do that in some sense the observer can jump in late enough that they essentially don't perturb the system until the Hawking photons have left the neighborhood of the stretched horizon. That is, if you try to, I'm sympathetic to the idea that there is something like that would negate this. But if experimentalists observe systems all the time, and they understand how to observe systems without perturbing them. And I think that in this case, one can, effectively do the same thing. That is, you can carry out the observations sufficiently late that you wouldn't expect to produce large perturbations. But this is not something I can prove. It's something I've kind of considered individual instances of what might go wrong, and I can tell you that again there are people who believe as you do, though they have not yet produced a calculation. Yeah. Actually, I should say good. So Samir Mathur, who again did a lot to refine the paradox, who proposed an idea I'm going to talk about soon, also believes that something like what you said is true, and has just put on the archive in the last week a model, a refinement that proposes to do something like what you said. I haven't yet digested it. Yeah.
Again,
yeah.
it seems to me that I would object to any of these arguments if there wasn't any observer actually doing any observing.
Right, but again, like I said, experimentalists observe systems all the time, and merely having an observer doesn't. There's a reality that they're observing, and you have to ask. You have to identify a specific way in which the observation disturbs the system, which I don't think has been done.
Right, but we're talking about specific observers and how pull through the horizon.
Yeah. Well, again, is a photon an observer? I mean, is there some reality to what happens to a photon if I fire it through the horizon? Good. Then we're on the good. That makes it good. So let me continue, and we can carry on later on. So if we give up the entanglement of these two bits, okay, we're no longer in the adiabatic vacuum. So this adiabatic principle that I was praising is now lost somehow. And what it means is there is a high energy particle in a regime where there's no ordinary mechanism to produce it. And how high in energy? Well, basically, you can, as you follow these back and back, their energy was higher and higher. There's a point beyond which, say, the Planck energy, you wouldn't follow them. But if you trust effective field theory back to just below the Planck scale, then this loss of entanglement would say, as you fall through the horizon, you have some chance, much larger than the adiabatic principle would allow to encounter a high energy quantum. And now there's a question. There's technicalities as to whether these quanta. The strictest form of this argument requires only that they appear in the S wave, meaning they could be anywhere around the horizon, and you have only a power law small chance to see them, which is much bigger than the adiabatic principle allows. Or there are more refined arguments which suggest that they're kind of everywhere around, that these or some other disturbance are everywhere around the horizon. So that's the firewall, a whole shell of particles of high energy particles where the adiabatic principle doesn't allow them. Now, having come to that ridiculous, and it is a ridiculous conclusion, we can ask, are there any mechanisms for this? And I'll give you three potential mechanisms. One of them is, we know in other contexts that if we have a singularity, it can expand into a shell of brains. That in fact, this is how string theory deals with certain singularities. Now, in the cases that we understand, these are time-like singularities, and so this process is causal. For the black hole, these are space-like future singularities, and so this expansion would be backwards in time, which doesn't sound very nice. But what might be happening instead is, rather than an acausal expansion, is some tunneling process. So, we haven't ever talked about the black hole singularity because it's in the future, but it's something you might worry about. So Mathur has proposed that there is some tunneling process that effectively produces a shell of brains on the horizon. And okay, I don't have much more to say than that. Real calculations are lacking, but but this would be, again, some kind of disturbance on the horizon that he also believes that there's a dual framework in which you can fall through. I don't think that's possible, but this is another model for what might be happening. Second model is replace the brains with strings. So we know that strings see space-time geometry differently from point particles. Things like mirror symmetry and T-duality are examples of this. Now, at the black hole horizon, there is something funny going on because there's an enormous boost between the initial body that formed the black hole and the frame of a typical late-time observer. But in quantum field theory, a large boost between things that are far away from each other has no big effect. Doesn't cause effective field theory to break down. If you have two things that are highly boosted on top of each other, of course, there's a big effect. But strings are weird, and it might be. No one has ever really done reliable developed technology. It might be that strings are sensitive to large boosts even when they're non-local. And so Silverstein and Dodelson have done a series of calculations which, building on old intuitions of Susskind, which suggest that maybe, in fact, the reason that the horizon is singled out as this place where some kind of dramatic physics happens is because of this non-local property of strings. I throw that out. We're talking about scenarios now, by the way. We've dropped from, calculations to no-go theorems. Now we're on scenarios. And the third scenario, which is sort of the one I like best, is even less well-defined. It's that, in ADS-CFT, space-time is emergent. The basic bits, the things that live in the gauge theory, the fact they can organize themselves into space they can do this, but we don't understand how they do it, and that is, face it, maybe they don't always succeed. Maybe the conditions for those bits to organize themselves into a smooth space cease to hold past the horizon, or cease to hold past this argument, by the way, I should say, only requires, so there's the Page curve and the Hawking curve. It's only past the half-life of the black hole, past the Page time, that there's a discrepancy. And so only for old black holes is there a contradiction. And so it's possible that whatever happens only for old black holes. But the words I like the best that have the fewest equations that yet go with them is that simply space in the interior fails to emerge. Okay, so this was so actually when you give up 4, there's 2 ways to give it up. The first way is it's fiery or brainy or stringy drama. It's something. It's the black hole horizon not being as Einstein's theory says. There's another kind of drama which has surfaced in most of the people who are trying to figure out how quantum gravity could avoid this conclusion instead introduce what I call quantum drama. So let me give you an example of quantum drama. And I think this is the last thing I'll say, and it won't take very long. Suppose I give you 100 spins, 100 spin-and-a-half particles. And I won't draw them all. And I tell you that I've prepared them in such a way that if you measure their spin along the plus z-axis, you will get plus a half. But also I've prepared them in such a way that if you measure their spin along the plus x-axis, you will get plus a half. Each of them has been prepared in this way. Okay? That is so. And you choose 50 at random. You choose 50 at random, and you measure the z component. You find it's plus a half. The other 50, you measure the x component, and you find it's plus a half. You should be very disturbed by this, of course. Tom is disturbed because this is not how spin-and-a-half particles work. If it's definitely in the z direction, then it's 50-50 to be plus x and minus x. Actually, this is a little even spookier because you can measure the x spin first and then the z spin and get the result that I just asserted. But if you measure the z spin first and then the x spin, it doesn't work. So there is a framework that produces this, which is imposing a final state boundary condition on your physics. So the normal observations are you have your operator and you have the state of the system. I'll call it rho sub s for system. And this is the probability of observation. In final state quantum mechanics, you impose also a final state boundary condition. I think I haven't written this quite correctly, but it gets the idea. You require a definite final state. Yes, that's what they're doing. That's what they're doing. Exactly. And so in this case, of course, my rho sub s is a state in the plus z direction. My rho sub f is a state in the x direction, and so whether I measure s sub z or s sub x in one direction or the other, I'm in an eigenstate. Now that sounds really weird, and it is, except inside a black hole, we've got this future singularity. And if we had a past singularity, we wouldn't be surprised if there was a boundary condition there. And so about 10 years ago, Horowitz and Maldacena, I told you he was speculative, proposed, well, if there's boundary conditions at past singularities, then there should be boundary conditions at future singularities as well. And if there were, then in fact the information paradox goes away, but you encounter what I've called here quantum drama. And it should disturb you much more than merely burning up in a bunch of, this is really weird. This is much more disturbing than just burning up or running into a bunch of brains. And also there is this question: can it even be consistently formulated once you're past the horizon? And indeed, there isn't but there is a certain appeal to this idea. And there was even before the firewall came along, and maybe there still is. But I mentioned this as an example of quantum drama, where the observer who passes through the horizon. So in Hawking's modification of quantum mechanics, the observer at infinity saw modifications of quantum mechanics. Here, the observer who passes through the horizon, they see, or at least their basic description, their basic laws, somehow involve not the usual laws of quantum mechanics. And so when we give up the no drama, there's these two kinds of drama: the one where you burn up, and the quantum drama. And there's other kinds of quantum drama. And so in my final lecture, I'll say a few more words about this, and then there's two things I want to talk about. One of them is chaos and its connection with this, and the other is bulk reconstruction and its connection with this. Thank you. More questions? Yes?
I didn't see the argument for putting a boundary condition on the but that's what I'm singularity. Because I mean, if we have a past infinity, we would put a boundary condition there. We can put another boundary condition at future infinity, right? In normal states. Why?
So it's sort of just democracy of singularities is the argument they made. But there's a picture which seems persuasive until you poke on, which is the way the information gets out is it falls in, hits the singularity, and bounces out again, and then propagates forward. So I mean, I have to say this is a nice picture, which would be nice to attach equations to. But it's true when you try to actually, when you try to actually attach details to this. It's not, and I mean, in fact, so Preskill and Gottesman, pointed out when you start including interactions between these two things, you effectively have a closed time-like curve. And I liked this when I first saw it, and every attempt to develop, there's only a small number of papers, Preskill and Shore, Douglas and someone. Every attempt to develop it just doesn't make it seem to get better. It makes it seem to get worse. It's kind of like Technicolor. Yes. Yeah. No, that's my model of something which you see the first paper and you think, wow, and then it just I mean, there are ideas like that, right? Yeah. Ben, yeah. Actually, I actually am not even sure, and I'm not sure whether they're sure, whether it's in the category of something that happens sharply at the horizon, or something that that is visible a distance of order 1 away. So I think it's still they've they've calculated these. You kind of need 6 particles to get this effect, because you need 2 incoming and outgoing, and then a probe particles, and again, they claim to see something which is acausal by the usual standards of particle scattering, but I don't yet know. I don't know. Yeah. Here. Yeah.
What happens to a string getting close to the horizon and part of going through it?
Well, I mean, a horizon is sort of rushing at you at the speed of light. You can't really do that for very long. I mean, part of right. So, so early on, I mentioned that we all know that as you fall through the horizon, someone who sits at infinity, if they could see you, they would see you hung up on the horizon forever. And in some ways, that nonlinearity in time is the origin of Hawking radiation. Susskind pointed out that in fact, because of the slowing down, the string, if you could see it, you'd see it getting bigger. And it was never clear what kind of role it played. Actually, tomorrow that effect will play a role. It will play a role in this chaos story. So in the chaos story, in fact, there's a sense in which someone at infinity can see the person falling, can actually, the person falling through the horizon, even though they seem to be black, there's a way in which they can affect the measurements of someone who is looking much later on. And so, we'll come to that.
So, can I think of the horizon as a Berlin Wall? You were talking discussion getting close to the wall and checking in.
Yeah.
You can pause what you're going to talk about tomorrow.
So the main I used the words earlier, information-free horizon, and the adiabatic principle says that an unfolding observer falls through empty space, falls through a vacuum. This, however, this chaotic behavior of the black hole implies that they actually are falling through, in some sense, a stream of information. That there is something. I'm not so much answer. I'm not sure how to put it in how to use the Berlin Wall metaphor, though I'll try to. It's a good one. Pre-89 and post-89. Anyway, I'm jumping. I don't know what to say. I'm jumping ahead. Yeah. So let's see. We're on time. Okay. Actually, we should go to lunch and take questions privately. Oh, we should go to break rather. Yes. I'll go to lunch. Thank you. Yeah.
I want to understand better
Yeah. Good. Yeah. But first, a question from a student. Yes, sir.
I have a very stupid question. When you draw the two Hawking quanta,
Yes.
why is it parallel?
Okay. Oh, good. Yeah. It's because good. So if you right. The Hawking quanta are not doing this. They're doing this.
Wow.
So if you think about the